Hi, my name is Nico, and today I'm going to present to you MIPS Project Ryu. We'll start with an introduction as to why it's called Project MIPS Ryu. We'll go into the instruction set architecture, including the register set, the data types, the instructions. Then we'll go into the enhanced instruction set. We have a special example for you today with that. Then we'll do system hardware diagrams, and then future enhancements, and any questions you can ask during the presentation, but if you have any more at the end, we're welcome to take questions. So, in Japanese, the Ryu, they are Japanese dragons. They're often associated with water, and they're long, serpentine, legendary creatures. The MIPS Ryu is a unique build of the MIPS ISA. It has powerful SIMD instructions. MIPS Ryu is powerful, dragons are powerful. It's streamlined for data processing, which relates to water. Dragons are related to water, and so it's streamlined. And it's also fluid and adaptable because of the structure we call the Ryu. The Ryu is the register interface unit, so MIPS Ryu is a play on sound because they're both Ryu. So here's an overview. We have the memory architecture, the register set, data types, and addressing modes, and then we have our instruction set. This is the baseline of every instruction set architecture. So the memory architecture we're using in this system is the Harvard memory architecture. It means we're using separate instruction memory and separate data memory. We're using big endian, which means that the big address is stored in the higher address. We have a maximum 32-bit address data line, and we also implemented a stack structure using push and pop operations. Push uses pre-decrement, and pop uses post-increment. And we'll go into the instructions we added push and pop later in the presentation. We have a general purpose integer register set. We have 32 registers for that. We have the SIMD register set. This is for the vector operations. Each register is 128 bits wide, and you have 32 of those. There's the program counter register, the high and low intermediate registers, and the SIMD buffer register, which we are calling the Ryu. It's what allows us to communicate between the integer data path and the SIMD data path. And there's another Ryu we use to talk between memory and the SIMD data path. So we have four major data types. We have the signed integer and the unsigned integer. So those are both 32 bits. We have a signed long integer, which is the result of multiply operations. You can use both of those separately and simulate 64-bit operands. But for the most part, most people wouldn't be using two 32-bit registers separately. And we also have vector signed integer, which is what the SIMD unit uses. We have three major addressing modes. You have register correct. It's defined by the 5-bit opcode, 5-bit field in the instruction. We use it for R-type and I-type. Register indirect, which is used mostly for load words, store words, branches, and immediate operands, which are defined in I-type and J-type instructions. So here we have our instruction set architecture, a flowchart, a pie chart representing the breakdown of instructions. 29% are R-type, 24% are I-type, 3% are J-type, and we have 44% are enhanced instructions. and a breakdown of each one. We have SAMD R-type, enhanced R-type, and SAMD I-type. So the new instructions we add are 17 more SAMD R-type. They're much like the R-type. There's vector add, vector subtract, vector multiply, set less than, and then there is SAMD I-type, load word, store word, add immediate, set less than, and set less than unsigned immediate. And then there's helper functions which let us communicate from the REU between the IDP and the SIMD unit. And then we've also added 2 more instructions, push and pop, and it helps us simulate a stack structure for programmers. Makes it easier to program. And each instruction takes between 3 and 8 states to complete. And here's a breakdown. We'll use these numbers later in one of our examples to highlight how much better SIMD is than the baseline. A few things to note are that there's new instructions, fill vbuff and fill vbuff v. Fill vbuff I moves from the integer data path to the vector data path through the REU. And the other instruction, fill vbuff v, moves from the vector unit back to the integer data path. And in addition to those, we have pop vbuff and push vbuff, which moves from the REU to the appropriate either IDP or the SIMD unit. Other things to note are that load word takes 7 instructions, 7 states to load 4 operands, whereas the normal load word would take 4 states. The normal store word would take 4 states to load 1, so it would take 16 states if you wanted to load 4 separate pieces of data. And in order to add these new instructions, we had to add three new instruction types: SAMD R-type, SAMD I-type, and enhanced R-type. SAMD R-type is much like R-type, except the field, the opcode field is 1F instead of 00. Mm-hmm. The SAMD I-type is much like I-type, except instead of a 16-bit signed immediate, it uses a 10-bit signed immediate. And the enhanced R-type is also much like the R-type, except it adds a new field, RU, which you're able to use for 4 registers instead of 3. So before we continue, do we have any questions on what has been presented so far?
For your SIMD I-type, so you know how you have 16-bit for regular I-types, and then I think you said 10-bit immediate
Yes.
for SIMD. What's the other 6 bits being used for?
That is used for the function code.
Function code. And then what's the opcode used for?
The opcode is what defines it as an enhanced instruction. All enhanced instructions begin with the field 1F.
1F? Okay, gotcha. Thank you.
So the reason we're using push and pop is because they're very common operations for programmers to use. Push uses pre-decrement and pop is going to use post-increment. So programmers use push and pop a lot when they're doing context switching, when they have to jump from one process or one command to another command. They have to push registers from the integer register set onto memory in order so that these registers can be used for other purposes. And also, push and pop are used for storing temporary data, as in an example in RPN calculator. And also, push and pop would allow programmers to easily represent stack and other data structures. And push and pop, they combine the increment and the decrement into the instruction so that programmers don't have to call another instruction to do the same operation. Now we're going to talk about why we're using vector SIMD. Vector SIMD is the main highlight of MIPS RIU. So SIMD stands for Single Instruction Multiple Data. So each instruction is able to operate on 4 words, 4 32-bit words. So vector SIMD would be useful for computation-heavy algorithms. So integration and summation, major calculus features like this would be very useful to have SIMD incorporated into that. And we'll actually go into an example with that today. Matrix manipulation would also be another thing you can use it for, such as computing echelon form. And also for calculators, if you're doing a whole bunch of graphing and you have a defined equation, you might use SIMD to quickly compute all the points. Or if you had a spreadsheet where you have to have a predefined formula on each cell has the same general formula but different data, you might want to use SIMD to speed up the process. So, trapezoidal integration. It's one of the major calculus integration methods. It's very simple, but for a computer to do, it requires a subtract operation, an addition operation, and a division operation, and a multiplication operation. So 4 operations, and if you have more data points, it's going to get a lot more difficult, a lot more processes, a lot more states in order to compute that data. So here we have a simple example of an Excel sheet, what one might use like a trapezoidal integration problem. So here we present to you the code for SIMD and Baseline. Well, the SIMD code has a few more instructions in order to load the initial registers. It's able to complete the operation much faster, as seen by this chart. For vector SIMD, we would have for 64 iterations, we would have 1,290 states. But for the baseline, that would take us almost 4,400 states. So that's an increase of about 70%. We have 70% less states. So the major modules we're using are the CPU, the central processing unit, the IDP, the integer data path, the MCU, the MIPS control unit, the instruction unit, the register interface unit, and our SIMD data path. And for external modules, we have external memory and external I/O. So here's an overview of the top level. So there are 2 RIUs, one for memory and one for communicating between the IDP and the SIMD units. So the reason why we use this structure is because the IDP can calculate instructions separately from the SIMD instructions. So there's 2 data paths, so that if we did have a pipeline, we'd be able to use both of them concurrently. For the number of pipeline stages it would take a lot more than 5 states for the baseline, which the baseline would use 5 states. But this, as it has more processors, it would take a few more states. And here's a closer up version of our CPU module. Now, here is our integer data path module. The additions we've made to this processor are that the T output, the ALU output, and there is now a S output. All of those are tri-state, so that there is no bus contention between itself, the IDP, and the SIMD units. There's the new S output, and that goes directly to the S RIU. And the ALU out would go to the memory or the I/O address, and the T out would go to the data for memory and I/O. Here's our instruction unit. The one addition we have to this is the sign extend 10. This is what we use for our SAMD I-type instructions. And here's our REU. The REU is much like a IDP. It has data going in, it has a function, it has 8 functions. Some functions are for flooding each of the words. So one might put, like, register 1 is loaded with FFFF. So all 4 words, word 3, 2, 1, and 0, would all be loaded with the same value. That's one function. Or there's rotate operations, and there's load individual words, which is useful when one is communicating between the 32-bit structure and the 128-bit structure. It allows one to easily communicate between the two.
What are the 3 sources for the Ds up top?
Good question. That was an earlier design choice when originally vectors were going to have each word of the vector was one of the D choices. Future enhancements, though, would limit that down to 1 D input in order to reduce the cost of creating the CPU. That's going to be a future enhancement, though. We haven't implemented that design yet.
But I'm assuming some way it's coming from the integer data path into the SIMD unit? Is that the purpose, or no?
The D inputs would be the S outputs of the vector unit. So it would be bits 128, 96, and then 95, etc. So in future enhancements, we're going to reduce that down to 1 32-bit D input in order to reduce the cost of creating the module.
Good, thank you.
And here's our SIMD unit. The features are 4 ALU units, 4 32-bit ALUs. It has high-low registers, so you can save your multiply and divide results. And it also has the tri-states on the ALU out, the T out, and the S out, so that there's no bus contention when it's communicating with the IDP unit. And here we have our ALU. It has the MIPS unit, the multiply, the divide, and it also has the barrel shifter. And flags, for unsigned operations, flags for the zero flag, for the negative flag, they're set to 0. That's why we have the N flag mux.
Can you go back to that, Nick, while we're in the flow of that?
Yeah.
So that's the same ALU that's instantiated 4 times in the SIMD?
Yes, and
so then you've got 4 sets of flags?
the flags are unused
Okay.
for SIMD.
Okay.
So future enhancements would be floating point. We're planning on adding 64-bit floating point data, and that would be both in a coprocessor, so we would have 3 processors, the integer data path, the SIMD data path, and the floating point. But we would also modify the vector data path in order to incorporate floating point into it as well. In addition to floating point, we would add vector merge, rotate, and permutate functions in order to allow matrix transposing and rotation to be facilitated by those new functions. We would add utility functions such as decrement jump not 0, jump carry, add with carry, and shift left logical with carry. Those are just a few. And we would also pipeline this architecture in order to increase the throughput even more than we did. Any questions?
None. Excellent job. Excellent.